So now we're going to learn about rectification. So what is rectification? Rectification is the process of converting AC into DC. So why do we want to convert AC to DC? It's because some appliances or some electrical components, they can only operate on DC. Example, handphone chargers, diodes, all these will operate on DC. So if you want, it's not a diodes, LEDs, LEDs and what else? LEDs and handphone chargers all operate on DC lah. So if you want to have DC, the simplest way to convert AC to DC is through half-wave rectification, which is actually using a diode connected in series with the supply and the load. So what will happen is, imagine the supply gives you a sinusoidal AC, and this voltage that we are measuring is the voltage across the resistor. So let's call this R. So this R, and this is the voltage across the resistor. Alright, so the question is, how will the voltage of your resistor vary with time? So every time the current flows this way, because voltage is positive, so current will flow this way. So it will allow current to flow through a resistor, so there will be a PD. But when the supply voltage reverses, then it tries to flow this way, the diode will prevent it from flowing, so then this part will be cut off, because there will be no current, so there's no PD. So half the cycle you got voltage, the other half cycle it prevents it from flowing, so there's no more PD. Alright, so it's called half-wave rectification. Now half-wave rectification is not very efficient, because if you find the average voltage, it will be between here and also 0 as well. So it'll be slightly less than half. Okay, the average voltage. So the average power is also less than half of the maximum power. Okay now. So the better way to change AC to DC is using full wave rectification. So full wave rectification is achieved using what we call as a full wave bridge rectifier, which consists of 4 diodes. So these must be 4 diodes and must connected correctly, then only will give you full wave rectification. Example, you notice that after full wave rectification, your supply, which is an alternating voltage, will now become direct voltage. It means just one direction, but still fluctuating, but still one direction. But you don't cut off anything, it's just continuous. So how do you achieve it? Right now, these 4 diodes must be connected correctly. I'll show you how to connect the diodes. Now, if you draw this like a diamond shape, you draw the 4 diodes, right? You notice that they're all pointing generally in the same direction. This one's pointing to the right, pointing to the right, pointing to the right, pointing to the right. So they all must point in the same direction. Now, if this one points to the left, then this must be the left, this must be the left, this must be the left. If this one pointing down, then this is pointing down, pointing down, pointing down. Pointing up, pointing up, pointing up. So they must all same direction. Depends on where you connect it. Example, if I'm connecting my diode, right? How do I do? Now let's say I draw these 4 diodes. Do you notice they're all pointing to the right? So can you see it converges at this point? Where it converges is where you must connect it to your load. So the opposite terminal to where it converges, which is this, also connected to the load. So always remember, after you draw the diodes, then you see where they all converge. So first you must determine which direction you want to draw. That means it's to the right, means all to the right. If to the left, all to the left. So where they converge is where you connect to your load, and the opposite terminal also to your load. Now the remaining 2 terminals is to your supply. That's how easy it is lah. So if you drew up, 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 so they converge here. So this must connect to load, opposite connect to load, and opposite these 2 will connect to supply. So that's how you do it. So in this particular example, how does it work? Example, now if let's say I give this as a positive and negative, right now. So when this is positive and this is negative, current will flow out from the positive, right now. So current will definitely flow here, because it cannot flow here because the diode is reverse bias, so it flows here. Then it cannot flow here, so it flows here. So you notice that the current is this way. Agree? Then what will happen is it reaches this point. Now from this point, there are 2 ways to flow, either through here or here, both also forward bias. But it will only flow here and not to here. You know why? Because after the current flows through the resistor, wouldn't the potential drop? So the potential here and here is the same, and it is lower than before the resistor. When the potential is lower, current cannot flow from lower to higher potential. This was before the load. You see that? It cannot flow back to higher potential. So it has to flow to the lower potential. Remember, this was negative connected to here, therefore it has to flow here. Same thing, when it reaches here, it cannot flow here as well because this is positive, higher potential, so it flows back here. So you complete the circuit now. But when you reverse the cycle, let's say this is now positive and this is negative. So this is positive, this is negative. So current will come out from the positive here. It cannot flow here because it's reverse bias, so it flows here. It cannot flow here because it's reverse bias, so it flows here. So you notice the current still flows in the same direction. So the voltage across the resistor, still same direction. Understand? So then it continues and reaches here. Okay, maybe I use, okay, it reaches here. Now it reaches here, there are two ways to flow. But flowing here means it's a positive, higher potential. But after flowing through a resistor, potential is lower, so it cannot flow back to positive, it flows to the lower potential, which is negative. And since this, it cannot flow here because it's higher potential, so it flows back to here, it's lower potential. So that way, it will conduct both, in whichever positive or negative, the voltage across your resistor is still the same direction. So you will also notice that in the beginning, when this was positive, I trace for you the current flow. It flows here, right now. So this is conducting, then flows to here, and then it flows through here. So this is conducting, right now. Then it flows out. So can you see that both diodes that conduct are opposite to each other? Now, then when you had this as positive and this is negative, so current flowed from here. Can you see that? So this is now conducting. Then it flowed through the resistor, then went back to here, and then it flowed through here. So this is now conducting, so opposite. So at any point in time, two diodes will conduct, and two other diodes won't conduct. It's always opposite to each other. You understand? So that's how you get your full wave rectification. But if you were to do rectification, would you be satisfied with this result? Having a big fluctuation from 0 to maximum, 0 to maximum, right now? So it's not a very good direct voltage because it's a big fluctuation. If you want to reduce the fluctuation, we use a process called smoothing. Now, if you want to create a smoother variation in the voltage, you don't want it to fluctuate so big. Then what you must do is you must connect a capacitor in parallel to your load. So your load is this, which is your resistor. So you need to connect in parallel. So you can draw here, doesn't matter, as long as you draw in parallel. So I put the capacitor here. Let me explain to you how this achieves smoothing. So remember, the voltage from your supply originally is this. After passing through a full wave bridge rectifier, it is this. So we're going to start from here now. So when it starts from here, I'm going to draw, after smoothing, it will be this. So how do I get this graph? I'll show you how. Now initially, when the voltage, so this dotted line, so let's look at the dotted line first. The dotted line is the unsmoothed rectified PD. That means it's this. It means without capacitor, this is the voltage that will pass through the resistor. Like, not voltage passing through the resistor, it's voltage across the resistor. It will vary like this. So now, when the voltage here increases, it is due to the supply. Everything is from the supply right now. So when the voltage is positive increasing, the current will be supplied by the supply and the current will flow through your load. That's why it gives you this voltage right now. But don't forget, the current can flow here, it can also flow here. So it means it can also pass through your capacitor. So that means as the current flows here, it gives you this PD, but also it passes through your capacitor, so it's charging up your capacitor. And it follows the same PD as this, which follows the PD of your supply. All three same. But when the PD of the supply reaches the highest and it starts to drop, the capacitor realizes that its PD is bigger now because it is at this voltage. But the supply PD starts to drop, but he is still at this voltage. So when this happens, the capacitor will now discharge across the load. So you see what happens initially when the current enters here. So this will be positive, this negative, right now. So when the current is coming out from your capacitor, it also comes out from positive and goes through this way. So it means it will still push the current in the same direction through your load. So this gives you also a positive voltage. But the voltage across your load will now follow the voltage across your supply. which is not supply, sorry, across your capacitor. Because now these two are connected, so this will be your EMF, this will be PD, so you follow the same voltage. So as the capacitor is pushing the current through your load, its PD will drop right now, and this PD will follow this right now, so it drops here. But it drops gradually. But by the time it reaches here, the voltage from the supply already dropped to 0, and then now it's going up. When it reaches this point, the voltage of the supply will now be bigger than the voltage from the capacitor. So then it takes over. So now the current will come out from the supply, push through the load, and also charge up the capacitor again. So that voltage goes up again. So when the supply PD drops, the capacitor will start to discharge and take over the responsibility. So the PD of the load will drop slower. So then here the supply PD takes over, and then as it goes down, the capacitor discharges. So therefore, you have this fluctuation already. So isn't it almost straight? So this is called smoothened or smooth rectified PD. Okay? So this is how it provides smoothing. So what are the factors that affect smoothing? Now you also need to know what are the factors that can affect the smoothing. That means how much smoothing you can achieve. Smoother means it will be less fluctuation. That means it will drop less. Less smooth means it drops more. It drops more. It drops more. So what factor affects the smoothing? There are two. The value of the capacitance here and the value of the resistance. Both will affect. Now let me show you the idea. Explain to you the idea first. First, how does your capacitance affect your smoothing? Now, capacitance in your topic of capacitance is Q over V, right now, charge stored per unit PD. So the higher the capacitance, the more charge it can store for the same voltage. Remember at the beginning, when it was being charged up, it will follow the supply voltage. So if your capacitance is higher, when you reach the same supply voltage, you'll store more charge. So when you store more charge, and when the supply PD drops, your capacitor is the one discharging through your load right now. But because it has so much charge, as the charge flows out your capacitor, its PD will drop slower because it has a lot of charge. If the very little charge and the charge flows out, the PD will drop very fast. So because of that, you get smoother. So how do we achieve a higher capacitance? The simplest way is to connect another capacitor in parallel. Because when you add a capacitor in parallel, you're increasing the capacitance. Now, what about resistance here? Your resistance also affects your smoothing. The higher the resistance, the smoother it is. You know why? Now, the supply PD will go up as usual, but if the resistance is high, the discharge current, that means when the supply PD drops, remember the capacitor is discharging through the load. But if the resistance of the load is very high, then the current will be small. So since current is also rate of flow of charge, if your current is small, that means the charge will flow slower. So that means the capacitor will also discharge slower, so the voltage will drop slower. So therefore, higher capacitance or higher resistance will give you a better smoothing. So better smoothing, how you would draw, is you will just follow the same curve, charging, because this must follow the supply, that doesn't change. So you must reach the peak following the same amount, and then you will draw a line like this. So this is smoother. If then you can continue go up again, follow the curve, and then go down here. Then you must follow the curve and then go back down here. But if it's less smooth, then you'll still follow this, but then it will drop more. But you must follow back the curve. You cannot draw a separate curve. You must always follow the supply PD during charging. Then it will drop more until it touches the curve, it follows the supply PD. Then it drops and then it follows the supply PD. That's how you draw for smoothing and less smoothing. So the shortcut in order to remember which factors affect the smoothing is using this formula, which is your tau equals to CR. Tau here is called time constant. Although it's not in your syllabus, but I find it very useful because time constant is talking about the time taken for the capacitor to discharge. By right, the actual definition is time taken for it to discharge the 1 over E of the original value. But you don't have to go so detailed in your syllabus. All we need to know is the time taken to discharge. The longer it takes to discharge, the smoother it is. The shorter time it takes to discharge, the faster it will drop, so less smooth it is. So use the formula CR. So that means higher the capacitance or higher the resistance, the longer it takes to discharge, so it's smoother. That's how you remember. Okay?